Hello everyone, myself Varun Puligilla. I am a technology enablement engineer from Tessent Siemens EDTA. Today we are going to learn some of the key features of Tessent IJTAG while performing automatic test pattern generation. This is the overall agenda what I am going to cover in this video. To begin with the motivation, it is to simplify the test setup procedure as well as the optional test end procedure to configure EDT IPs and any other embedded IJTAG instruments which are needed for scan ATPG. Here EDT is the embedded deterministic test IP. In order to enable IJTAG to set up embedded instruments inside the IJTAG network, you need to follow this flow. If you already have the design.icl, icl here is the instrument connectivity language of the icl network. If you already have that file, you don't need to perform insert IJTAG network or perform icl extraction to get the complete icl file. Similar to the previous step, if you're not inserting EDT IP in your design, you can skip step 2, that is the generation of icl and PDL for EDT IP. As I said, icl is the instrument connectivity language and PDL is a procedural description language. There are two different ways how you can insert EDT IP. You're going to learn that in coming slides. In addition to that, you need to provide the additional icl models if present, like tab or TDRs in your design, and then you can perform the icl extraction. Moving on to the IJTAG network insertion, that is IEEE 1687 standard. If you wanted to create your own IJTAG network, you can do that by connecting the existing instruments and insert SIBs, TDRs or scan muxes. SIB here is the segment insertion bit. TDR is a test data register and a scan mux. Tessent tool inserts a SIB or TDR based on how the icl models need to be accessed in the complete network. You should use extract icl to get the complete icl file of the design. Note you can also connect the network to the pre-existing tab controller in the design. This white box is the example steps on how you can get the icl file. You set up the context, you set the current design, you set the design level to physical block, sub block or top, that's chip top, and then you do set system mode analysis, that is you change the mode from setup to analysis. Here the check design rules is triggered. You create the DFT specification, process the DFT specification and then extract the icl. You'll learn more about create DFT specification and process DFT specification in coming slides. This slide talks about the general Tessent Shell flow, where it has two different insertion steps. In the first insertion step, you insert memory bist, boundary scan, and in the second insertion step, you insert EDT, OCC, and SSN. The create DFT specification command creates and validates the DFT specification wrapper. Process DFT specification creates and inserts the hardware which was validated during the create DFT specification command. After you do process DFT specification, you need to perform extract icl by triggering the extract icl command. You can find all of these files in the Tessent Shell database output directory. This is the second way how you can insert EDT in your design using Tessent test compress tool. You need to set the context to DFT EDT, and then you need an extra command called write EDT files in order to generate all the files like edt.v, the newly inserted design, tcd, icl, pdl, testproc, etc. You need all these files in order to enable IJTAG to set up this instrument. Moving on to the main part, setting up the embedded instruments. There are two ways how you can set up the embedded instruments. The first one is through test procedure. Please note that the IJTAG is only allowed in test setup and test end procedures, not in the ATPG's analysis mode. And the second way is through Dofile. Setting up the embedded instruments through test procedures file. What is a test procedure file? So previously defined scan clocks and any other control signals specify the scan circuitry operation. But in order to operate the scan circuitry in your design, the tool must have the specification of this scan circuitry and a test proc file. This is an example of test proc file for forcing the primary inputs, measuring the primary outputs, pulsing on a TCK signal, and the total time period of template. Here the icall is a PDL command. Icall is nothing but calling an iproc of an instance against its ICL module. The OCC inst1 is the instance name of the physical block or subblock in the current design. Like if you are providing this icall command to a block which is inside the current design, that is the physical or subblock, you need to provide the complete instance path here. But please mind that you need to source the design.pdl, that is the PDL file, in order to tool trace the complete path of this block. This is the output, how it looks like. Like after you provide these icall commands in the test procedure file, the resulting test procedure file would be like this. This is an example of PDL file for OCC instrument. So when you insert any instrument in the network using process DFT specification, you can view their PDL files in the instruments directory, which is under the Tessent Shell database output directory. Here setup is the name of the iproc. So when you icall the setup proc of the OCC instance in the test procedure file, as we have seen in the previous slide, the tool configs all the IRATs for this block. So here setup is the iproc name. This is registered against the instrument OCC. Sometimes embedding the icall commands within the test procedure file is not a convenient way, especially if they are generated from the tool based on introspection is not a convenient way. This is the second way by which we have all the design, introspection and tickle commands. Like these are available to specify the needed IJTAG commands. The set test setup icall and set test end icall are the two commands through which we can set up the icall to the procedure file. Set test setup icall adds an icall to the end of test setup procedure, whereas test end adds to the test end procedure. This is the example of set test setup icall where we have all these options to include. You can provide the ICL instance path, the iproc name, the front and end switches. By default, tool inserts the icall here in the middle. But if you wanted the tool to insert icall in the front or end, you can use these switches. Moving on to report procedures. If you wanted to view the resulting procedure, you need to change the system mode from setup to analysis by using set system mode analysis, or you can use the check design rules to change the mode from setup to analysis. And you should perform the report procedures after import scan mode. And if you wanted to look at the specific procedure, like here it's the load unload, you can provide this command report procedures load unload, and the resulting procedure would be like this, what you see in the terminal. And if you wanted the expanded iprocs, you can use report procedure expand iprocs. The expanded iproc looks something like this. It has the cycle information, it has the pin name, it has the ICL register name and few annotations. To end with the conclusion, the IJTAG ATPG flow systematically integrates and configures embedded instruments like EDT, OCC, and many other embedded instruments. This process ensures proper instrument setup via ICL and PDL files before the efficient automatic test pattern generation. This flow also offers the optional steps for ICL network insertion and extraction based on how your design is ready. As I said, if you already have the ICL file, you don't need to perform this step. So crucially, it allows for sophisticated instrument control during the automatic test pattern generation. Thank you for joining this presentation. This is my email ID. You can email to this if you have any other questions. You can also email to our application support engineers if you have more questions. Thank you.